Okay, hello everybody. Welcome to the CADimensions webinar on FDM Materials. I'm Lee McElhenney. I'm an application engineer with CADimensions, and I specialize in FDM Materials, processes, and applications. And hopefully today we're going to give you some insight on deciding which material is the best choice for your application. Before we start, let me just say that if you have any questions, type them into the bar, and we'll do our best to either answer them during this presentation, after the presentation, or we'll get back to you at some point and answer any questions that you have. First thing, we're going to start out a little bit of history with the company Stratasys. They are headquartered in Eden Prairie, Minnesota and Rehovot, Israel. They have over 1,200 employees globally with an expansive team of engineers that constantly work on materials and application advancements. They have over 65,000 printers installed worldwide in every sector of business. So what we'll do is we'll explain what the FDM process is. FDM stands for Fused Deposition Modeling, and it's basically kind of like a hot glue gun that extrudes out nearly molten plastic layer by layer to build up a product from the ground up. So it's the opposite of subtractive manufacturing, where you're starting with a large block of material and machining it away. Here with additive manufacturing, you're starting with nothing and adding to it to get your end product. So one of the benefits to the FDM process, or additive manufacturing, is that it removes a lot of the steps in the engineering process, streamlining the revision process and reducing tooling costs and time to market. The traditional process starts with an idea, goes to a design, then you have your prototype that has to be built. So prototype tooling has to get made, then prototypes get made, then revisions, starts the process over again, more prototypes, more prototype tooling, and so on for the number of iterations till you get to your final prototype tooling for testing, final revisions, and then your final product tooling. With the FDM process, or any additive manufacturing process, you go from your idea and design directly to a prototype. There's no prototype tooling. You're building your direct prototype. Then with that prototype, you can do your testing and revisions a lot easier. You don't have to make tooling each time. You make a simple revision, build another prototype, do more revisions, and so on. And then from there, in some cases, you can then build your final product. So it streamlines the process a lot. In the material world of plastics, there are a large range of properties. You have three different tiers of plastics, starting with your standard plastics, moving to your engineering plastics, and then high performance plastics. Within these three tiers, you can pretty much cover almost anything you need as far as requirements in toughness, thermal deflection, strength, and flexibility, and other mechanical properties. So within the tiers, your standard plastics are your ABS family, which is one of the more popular plastics in the manufacturing industry today. Moving up, you have your engineering plastics that cover polycarbonates and the new nylon materials. And then in the high performance, we have Ultem 9085 and PPSF or PPSU, depending on what you want to call it. These are the highest strength and have the highest mechanical properties out of all of them. Some of the common characteristics among all of them is that they are easy, clean, and safe. There's no dust or harsh chemicals in the production of any of the parts on any of these machines. They're very office friendly. You don't have to tuck them away in a shop or anything like that. The materials won't deteriorate over time due to environments such as UV breakdown or oxidation. They don't become brittle over time. So now we're going to go into how you select a material and what the properties of some of these materials are. One of the things you have to figure out is what are the boundary conditions, such as what strength do you need, what temperatures is it going to see, does it need to be sterilized, does it need to have a certain amount of flexibility or impact resistance. All of these are going to dictate which material you're going to want to use. Here's a general overview of the materials and some of the colors available within those materials. There are multiple choices of materials in each of the families of plastics, and that's going to help pinpoint what you're going to use it for. The first family we have is the ABS family. This is the most common thermoplastic used in the industry today and is the most popular for stratosys. ABS is available on any of the systems, be it the smaller dimension machines or the production series Fortis machines. Starting with ABS, we have ABS Plus and ABS M30. ABS Plus and ABS M30 are actually the same material when they're on the spool, but due to differences between the dimension machines that use the ABS Plus and the Fortis machines that use the ABS M30, the M30 has slightly greater mechanical properties just in how it's extruded. The ABS family of plastics are generally used for prototype models for fitment and finish, not anything where they're going to be specifically strength tested or anything like that. It's a quick, cheaper material to get something in your hand faster. That way, in the engineering process, you can go through ergonomic designs and revisions quickly and cheaply. This runs on all the systems, like I said, but the difference is slight mechanical and thermal deflection properties due to how it's actually extruded. ABS M30i is the first biocompatible medically certified material. It's certified with ISO 10993 and USP Class 6. It is optimal for use in the medical, pharmaceutical, and food processing industry because it's sterilizable. The different makeup allows for the sterilization, and it has the benefits because of that. This material is only available on the production systems, the Fortis 360 and up. The ABS-I is a very unique material that it's the most translucent out of all of them. You can see in the picture here, it was originally designed for the automotive and aerospace industries for taillights and things of that nature. So your color options are your amber, your clear, and your red. This is also good for monitoring material flow through a prototype of something to make sure everything is as it was planned, and that's also one of the benefits of it. This is generally not used in high strength applications. The mechanical properties are slightly less than the ABS as far as tensile strength and all of that. Next we have ESD7 ABS, and the ESD stands for electrostatic dissipation, or dissipative, and it has a surface resistance, target resistance of 10 to the 7th ohms, and depending on the size and the shape and the geometry, you will actually end up with somewhere between 10 to the 6th and 10 to the 9th. This is used in jigs and fixtures for electronic components where static charges are undesirable, or in situations where dust collection is undesirable, where a product is very sensitive to that. An example of that is our inhalers, and the reason they use the electrostatic dissipative plastic is that when it's spraying a mist through the body of it, there's no charge on the plastic to attract any of the mist, so more of the medicine is dispersed to the recipient rather than collecting and condensing on the inside of the inhaler itself. So it has a wide variety of uses, not just in the electronic world. Next, in the next family, we have our engineering plastics. These have higher strength and higher temp mechanical properties, and these are also used for jigs and fixtures that have a longer life or just see more use. The chemical resistance and heat deflection on these, as well as the strength, is greater than that of ABS, and these have kind of more unique application requirements than a jig or fixture that would be used with ABS. So the first in the family is the PC ABS, polycarbonate ABS blend. This uses a little bit of the best of both worlds of polycarbonate and ABS. It has a higher impact strength than ABS. It has a certain amount of flexibility, so it's great for impact resistance, and it has great surface definition, so they use it a lot in handles and bodies of power tools like circular saws and reciprocating saws and things of that nature that are going to get banged around and you don't want them to crack and all that. Some of the applications for these include the functional prototypes of those products, so they can actually design a saw, put it together, put it into use, and try the ergonomics in its actual used environment. It's also used in jigs and fixtures and assembly fixtures, work holders and stuff like that. So it's a little bit more flexible than the ABS, so it stands up to more use. The next thing we have is our polycarbonate. This is one of the stiffest materials. It has great strength properties and higher thermal and chemical resistance than the ABS family. It's the second most popular material next to the ABS. This is also used in jigs and fixtures and work holders for assemblies and stuff like that, where it's going to see a lot of traffic, a lot of parts going through it, and it needs to have a longer life. They also use these for certain tooling, for molds, things like that. One of the examples is Oric uses these as assembly fixtures, and they save $55,000 per vacuum series over traditional casting assembly jigs, just in this one application without compromising accuracy. So the printed part is just as accurate as their cast part, but they can develop the product more quickly and cheaply than traditional casting. Next we have PC ISO, which is our second biocompatible material like the M30i. This material has a similar function to PC, but it's sterilizable, so it's used in medical and food process applications and fixtures and jigs where they use food processing equipment, so the item needs to be sterilized and stay sterilized and just be clean. Like in the picture, you can see the blow molding jig for water bottles. You don't really want nasty stuff in there, so it has to be clean and sterilized. The next material is the newest material out of all of them. It's the Nylon 12. It was released in December, and the engineers are still discovering a lot of different applications and ways to use this one. So this is brand new to everybody. It's the first semi-crystalline thermoplastic that Stratasys has been able to extrude, and it already has a lot of great uses. It's very flexible, and this is just going to open the door for future material development. So I think they are going to try to get into filled nylons, be it glass or carbon or things like that. One of the best uses are flexible panels. It has the highest elongation to break of any material. It has an elongation of 30% before breakage, where the next most flexible material is PCABS, and that only has a 6% elongation. So this is a very, very flexible material. And we have a video here of a panel that they twist up, as you can see here. There he goes. And just its flexibility just can't compare to any other material that Stratasys has. Next, we have our high performance family. This includes the Ultem and PPSF materials. These have the highest chemical and mechanical properties of any material, and these are for the most demanding applications. The first in this, we have our Ultem 9085. It has great heat deflection to 333 degrees and the highest tensile strength out of any of the materials at 10,390 psi. It also carries an FST flame smoke toxicity rating, and that means that if the product does burn, it doesn't support combustion well, or it doesn't produce flaming drips when it does start to combust and melt. And the smoke has a low toxicity. One of the original uses for that were in the aerospace and transportation industry, where people are in a contained unit like a bus or an airplane, and if there is a fire, the smoke isn't very toxic and the material itself won't support, it doesn't burn very easily. It's also been used a lot in tooling, and I've seen it in low temp casting models where they actually build a metal casting mold out of it, and they use lower temp zinc based metals that have melting points of in the 200s. So it's still under the melting point of the plastic, so they can pour molten zinc based metals directly into it. It's also used for end-use parts where strength and fatigue resistance are key. This, like I said, it is one of the most mechanically superior thermoplastics that is used by any of the FDM machines. An example is Piper Airplanes uses this for all their metal forming tooling in the production of their airplanes. Then we have the PPSF or PPSU. It's polyphenol sulfone, and it has the highest heat deflection out of any other material at 372 degrees Fahrenheit. It has one of the highest chemical resistances and is designed around being used in conjunction with petroleums and solvents. It was originally developed for long-term automotive functional testing, where they design a part and they actually put it on a car or automobile, truck, whatever, for extended periods of time for the actual functional testing to see how the product works. And this is also sterilizable using gamma radiation, ETO, or an autoclave because it has the high deep heat deflection. These are also used for jigs where the assembly or the jigging process is used in very hot situations, or with hot, freshly cast or machined parts. This has the highest use in the aerospace and automotive sectors, and it's a really great material for those specific applications. So in summary, we have all the different materials. The ABS is ABSi is the translucent. ABS Plus is for the dimension type machines. ABS M30 is for the production type machines, and it's a little bit tougher. It has greater mechanical qualities. The ABS M30i is the biocompatible ABS. ESD7 is the static dissipative. PCABS is the impact resistant blend of PC and ABS. PC is a widely used, strong material for jigs and fixtures and stuff of that nature. PCISO is the biocompatible, similar to the M30i, but has greater strength and heat deflection characteristics. Nylon 12 is the newest and highest in flexibility and has great chemical resistance as well. LTEM is the generally mechanically well-rounded do-all material that's used in a wide array of applications, and PPSF is the highest thermal and chemical resistant. So if you have any questions, you can either email me, and there's my email there, or if I'm not available, you can contact Jeff Lewis, and we'll do the best we can to answer any of your questions. So we're going to open the floor now to questions, and I'll answer to the best of my knowledge. All right, guys, we'll talk to you later.